Students, in this note set, we're going to take a look at electron configurations again, but we're going to go into more depth. We're going to tackle some of the harder elements to write configurations for on the periodic table. First, let's take a look at the answer key to the homework assignment from last class. You were asked to write electron configurations for each of the first 18 elements. Now, I deliberately set up this page so that it would resemble the periodic table. In other words, the elements are found exactly in the same order as you would find them on the real periodic table. Notice that there's a pattern. Everything in column 1 ends with something S1. So hydrogen is 1s1, lithium 2s1, sodium ends with 3s1. The next column over ends with something S2. Beryllium is 2s2 and magnesium's 3s2. And in the third column, skip the transition metals for now. Third column, or group 13 on the periodic table, boron ends with 2p1. And right below it, it's aluminum with a 3p1 ending. Students, every single position on the periodic table has a unique electron configuration ending. Let me show you what I mean there. We're just going to look at the last sublevel. If you just look at the last sublevel listed, boron ends with 2p1, aluminum 3p1. Carbon ends with 2p2, silicon with 3p2. Nitrogen 2p3, phosphorus right below it 3p3. That's not an accident. That's not an accident. Every single position is reflective of its behavior. And you know from earlier in your study of chemistry that elements are grouped into columns based on how they react. So carbon will react similarly to silicon. Nitrogen will react similarly to phosphorus. Now, the noble gases, this is an interesting one. These are all non-reactive gases. Generally, in the noble gas column, you end with something P6. So neon is 2p6 and argon is 3p6. But what about this helium with a 1s2? It just so happens that in the first principal energy level, there's only one orbital, which means there's only one sublevel, which means it can only hold 2 electrons. So in the noble gas column, what you find are the elements that have a completely filled principal energy level and thus are unreactive. Noble gases don't react. Now, let's take a look at the full periodic table with all of those unique electron configuration endings filled in. Now, there are some goofy exceptions to a general trend, and we're going to ignore most of those. But just know that the goofy shape of the periodic table is reflective of the orbitals that are present in each principal energy level. What I mean by that is, remember what principal energy levels contain which sublevels? The first principal energy level only has one sublevel, it's the 1s. Thus, the first row on the periodic table only has elements with endings that end with 1s. The second principal energy level has 2 sublevels, the 2s and the 2p. Well, that means the second row on the periodic table has 2 sublevels, a 2s and a 2p. And the third principal energy level has 3 sublevels, 3s, 3p, and 3d. Now, it gets a little goofy here, and we're going to talk about the goofiness in a second. But in the third row in the periodic table, we have the 3s sublevel, we have the 3p sublevel, but it's not until you get down to the fourth row on the periodic table that you get to the 3d sublevel. Aha. And there's even intertransition elements which correspond to the F sublevels. Okay, now here's the big connection. Consider the types of sublevels that exist: S, P, D, and F. And you might say, well, what about G and H? They do exist, but they only are filled when an atom has excited electrons. Since we're going to assume throughout our study of electron configuration that we're only dealing with neutral atoms that are in ground state, we don't need to worry about G or H sublevels. Okay, so that being said, how many orbitals are in an S sublevel? One orbital. How many electrons, according to Pauli exclusion principle, can fit into any orbital? Provided they have opposite spins, you can fit two. Aha. 2 electrons can be accommodated in an S sublevel. Well, then it's no accident that in the region of the periodic table that we sometimes call the S block, there are 2 spaces wide. There's 2 spaces because 2 electrons can be accommodated in any S sublevel. What about the P sublevels? They contain 3 orbitals, each of which can hold 2 electrons. 3 times 2 is 6. 6 electrons that can be accommodated, 6 spaces in the P block on the periodic table. Let's count these. 1, 2, 3, 4, 5, 6. Oh man, isn't this cool? D sublevels hold 5 orbitals, each of which can hold 2 electrons. That gives us a total of 10 electrons that can fit. Thus, 10 spaces wide should be the D block on the periodic table. The D block is also known as the transition metals. Count with me. How many spaces wide is the D block? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is not an accident that the D block is 10 spaces wide. 10 electrons can be accommodated in any D sublevel. How about the F? The F sublevels have 7 orbitals. Remember the pattern of orbitals? S can accommodate 1, P's can accommodate 3, D's can accommodate 5, F's can accommodate 7. It's the odd numbers. Okay, 7 orbitals. Each orbital can hold 14 electrons. Thus, there should be 14 spaces wide in the F block on the periodic table. Now, the F block is also known as the inner transition metals, and because inserting it into the periodic table would cause the table to be really wide and really short, normally people just draw an arrow and say, hey, that's where the F block would be inserted. Let's count the number of spaces wide in an F block. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Not an accident. The periodic table has this goofy shape because it accommodates all of the electrons that can fit in all of the orbitals. Okay, let's go back to the periodic table. I just want to point out one more thing. Yesterday's assignment asked you to draw or write out electron configuration for elements 1 through 18. Now take a look at elements 19, 20, and 21. That would be right here. Potassium, what happens when you add electrons after the 3p? After 3p, so 3p is argon, and then we move to potassium, 1 more electron, you don't get 3d, you get 4s. For calcium, it's again not 3D, it's 4s2. It's not until you get to element 21, scandium, that we start to fill the 3D sublevel. And you might say, why? Isn't a 3 lower than a 4? Well, as it turns out, not exactly. The order that sublevels get filled reflects the energy required to hop onto that orbital's space. All right, to get the why, the full explanation for this, we need to think back to Schrodinger's wave function. In Schrodinger's wave function, we're considering the probability of finding an electron in a given region of space. And we can represent the probability, they call it radial probability. That means how likely are you to find the electron as plotted against distance from the nucleus. And it's not just a simple bell-shaped curve. It's not just a rise and a fall. There are other, what they call penetrations or humps near the nucleus that you can find electrons. Even though the most probable distance from the nucleus is way over here, a far distance from the nucleus, meaning far to the right on the x-axis, there are two humps closer to the nucleus, or penetrations, where electrons can enter that sublevel. This is for the 3s sublevel, 3 humps for the 3 sublevel, 3s sublevel. Now, take a look at the 3p sublevel. Okay, we have the major, this is in orangish color here. The 3p sublevel has the major hump, a far distance from the nucleus, but it also has a penetration closer to the nucleus. It's still not as close as the closest penetration for the 3s sublevel, shown in purple. And if you look at the 3d sublevel plotted on this same graph, shown in blue, there is only one hump, and it is quite far from the nucleus. The order that the electrons will enter sublevels is by the closest penetration. So electrons will jump onto the 3s sublevel prior to jumping onto the 3p sublevel, prior to certainly the 3d sublevel. Now, this graph would get a little complicated if we overlaid the sublevels for the 4th principal energy level, but there's a peak penetration closer to the nucleus before the 3D hump is found. And what that means is electrons will enter the 4s sublevel prior to the 3D sublevel. Here's a simple graph that kind of shows the order that you fill sublevels in. Remember, the first principal energy level only has one sublevel, and it's the 1s, and that is indeed the lowest energy level found. The second principal energy level has both the 2s and the 2p sublevels. And the third principal energy level, shown in green here, has the 3s, 3p, and 3d sublevels. But it just so happens that one of the sublevels from the 4th principal energy level, the 4s, is slightly lower in energy than the highest of the energies, highest energy of the sublevels in the 3d, in the 3rd principal energy level. Thus, the 4s fills before the 3D sublevel. And then it goes 4p, 4d, 4f. Energy is shown on the y-axis. Now, there's a nice little chart that anybody can make at any time. I encourage you, do not memorize this order of filling sublevels chart. Just write it out. Whenever you need to figure out the order that sublevels are filled in, make a list. And at the top of the list, write out the first principal energy level sublevels. That would be the 1s. And in the second line down, write the second principal energy level sublevels, 2s and 2p. And then for the third line, 3s, 3p, 3d. Fourth line, 4s, 4p, 4d, 4f. Fifth line, 4s, p, d, f. You could put a g after that, but we're never going to encounter g sublevels. And if you then draw strike-through lines from the upper right to the lower left and follow the arrows. So if I'm starting with 1s and then I go to the end of the arrow for this diagonal arrow next, I have the 2s, and so on. You'll get all the And you can go for quite a ways, all the way to the 8s sublevel and even afterwards. Now, students, we're not going to bother going for really, really big and rarely seen elements. We're going to mainly focus on the ones that we normally see in chemical reactions. Okay, let's try a sample problem. Let's say we're asked to write the electron configuration for potassium. We're going to assume that the atom is neutral and is in ground state configuration. That means no excited electrons. They're all as close to the nucleus as they can be. The first thing we'd want to do, if given this problem, is find potassium on the periodic table. There it is. Potassium has an atomic number of 19. That 19 is going to be the most important thing to think about when we tackle this problem. The next thing we want to think about is, okay, we've got to find a home for 19 electrons, because if it's a neutral atom, then there's the same number of electrons as protons, 19. And then we need to think about the order of filling those sublevels. 1s followed by 2s, followed by 2p, then 3s, 3p, then 4s, 3d, 4p, 5s. Follow these strike-through lines to follow the order. Now, the other thing you should keep in mind is how many electrons can fit into each of those sublevels. If it's an S sublevel, only 2. If it's a P sublevel, 6. If it's a D sublevel, 10. If it's an F sublevel, 14. It's always 2 times as many electrons as there are orbitals within that sublevel. In this particular case, we'll find that the 4s sublevel fills before the 3d sublevel. So when we're finding a home for the first 19 electrons in potassium, electron number 19, after you've gotten to 3p6, it's not going to go, as some people may be tempted to put, 3d1. No, it's going to go 4s1. Check it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Remember, the sum of the superscripts in the electron configuration is equal to the number of electrons. So let's do a little mental math here. 2 plus 2 plus 6, that's 10, plus 2 plus 6 plus 1, that's 19. We've found a home for all 19 electrons in neutral potassium with this configuration. Can we try another? Absolutely. Let's say we're asked to write the electron configuration for zirconium. And again, we're going to assume that the atom is neutral and in ground state. First, find zirconium on the periodic table. I'm going to give you a minute to look at your periodic table and find zirconium. It's Zr. Element number 40. If the element's number, the whole number in the box is 40, that means there's 40 protons. We're assuming it's neutral, so there will be the same number of electrons as protons. Remember the order of filling the sublevels. 1s, 2s, 2p, then 3s, 3p, then 4s, then 3d, 4p, 5s, then 4d. Of course, you notice that zirconium is in the D block on the periodic table. It's in the second row of the D block. So think of which principal energy levels can have D sublevels, so third principal energy level or higher. Well, we're in the second row of the D block, so we're at the second principal energy level that has a D sublevel. That's the fourth principal energy level. Furthermore, we're in the second column of the D block. So you would expect the config to end with D2. right? Well, let's follow the order of sublevels until we find a home for all 40 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. 4d2 is the ending. And it's exactly what you would expect based on zirconium's position on the periodic table. Okay, little mental math here. You might even want to pull out a calculator for this one. 2 plus 2 plus 6, that's 10. Plus 2 plus 6 plus 2, that's another 10. Plus 10, that's another 10, so we're at 30 so far. And then we're going to add to that 6 plus 2 plus 2. That's 40. We found a home for all 40 electrons for zirconium. Good job. Now, a couple of things. We need to teach you a shortcut. I'd say it's time, right? You've written some very long electron configurations. This can get tedious. As we get to the bigger elements, as you go further down on the periodic table, the configs, there's a lot to write. There's a lot to write. We can abbreviate. We're going to abbreviate the elements configuration by writing the symbol for the previous noble gas. So you've got to go backwards on the periodic table from the element that you're considering and write that noble gas's symbol and throw it in brackets. And then write whatever comes after that. That means you really can cut down on the writing here. Let's give an example. Let's say we're asked to write the configuration for sodium. Sodium is element 11. And it wouldn't be the end of the world. I mean, this one's not going to take you an hour to write out. But if it can save some time, then it's worth some time to figure out the shortcut. The noble gas that precedes sodium on the periodic table is neon. Neon is element number 10. Neon's config, if you were to write it all out, it'd be 1s2, 2s2, 2p6. So that would be the 10 electrons of neon. Well, suppose we want to write sodium's configuration just a little bit shorter than usual. Instead of writing out 1s2, 2s2, 2p6, 3s1, you could just put neon's symbol in brackets and then what comes after it, 3s1. So it's like neon's configuration, which I don't want to write out, and then what follows, 3s1. Let's go back to potassium. Potassium's full configuration that we had worked out a couple of minutes ago was 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The noble gas that precedes potassium on the periodic table is argon. Argon is element number 18. Its config, if you were to write it all out, would be 1s2, 2s2, 2p6, 3s2, 3p6. Notice all of these sublevels are filled in the same order every time. Gee whiz, couldn't I just say 1s2, 2s2, 2p6, 3s2, 3p6? I just want to write argon. The AR for argon in brackets represents all of argon's electrons. So we can shorten potassium's configuration. Instead of writing all of this business up at the top, just write argon in brackets and 4s1. Let's check out zirconium. Zirconium's full configuration was all of this. Yeesh. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. The preceding noble gas to zirconium is krypton. Krypton is element number 36. Okay. Krypton has all of these electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Well, let's just plug that into what we had up at the top. You can shorten zirconium's configuration to just Kr, krypton's chemical symbol in brackets, followed by 4s2, 3d2. Oops. Hang on. I got it. It's a 5s2, 4d2. So whatever follows the 4p6, 5s2, 4d2 is what comes for zirconium. Here's a simple summary of all of the noble gas shortcuts. So if helium ends with 1s2 and neon is element 10, it would have helium's contents plus 2s2, 2p6. Argon would have neon's contents plus 3s2, 3p6. Krypton would have all of argon's contents plus what follows, 4s2, 3d10, 4p6. Xenon would have all of krypton's contents plus 5s2, 4d10, 5p6, and then so on. And you can get low down on the periodic table, and you can get a lot of electron configurations. Can be very long. I'm trying to minimize the tediousness by giving you the shortcut here. Okay, last little bit. Let's say I'd like you to write the electron config for tin, whose symbol is SN, using the noble gas shortcut. I'll give you a sec to find that on the periodic table. SN, tin. It's element number 50. Element number 50. So if it's element number 50, we presume a neutral atom. Then you'd have the same number of electrons as protons. We'd recall the order of filling sublevels. And I'm encouraging you to think about the noble gas shortcut. Oops. Write the symbol of the preceding noble gas in brackets. So on the periodic table, count down from 50. What noble gas comes before 50? Don't count up to 54 xenon. Count down to the previous noble gas, krypton, that's element number 36. And then if you write krypton's symbol in brackets, and then what follows, you'd have 5s2, 4d10, 5p2. And that's not surprising. Look where tin is on the periodic table. It's in column 2 of the p block. Of course it's going to end with something p2. And if the p block has rows for principal energy levels 2 and higher, then we're in the principal energy level that follows krypton, the 5th principal energy level. I'm going to invite you to try this on a homework assignment, and thanks for your good attention today.